In algebraic geometry, a morphism between algebraic varieties is a function between the varieties that is given locally by polynomials. It is also called a regular map. A morphism from an algebraic variety to the affine line is also called the regular function. A regular map whose inverse is also regular is called biregular, and they are isomorphisms in the category of algebraic varieties. Because regular and biregular are very restrictive conditions, there are no non-constant regular functions on projective varieties. The weaker condition of a rational map and birational maps are frequently used as well. Definition: if x and y are closed subvarieties of an enam, then a regular map f(x, y) is the restriction of a polynomial map enam. Explicitly, it has the form where the s are in the coordinate ring of x. The ideal defining x, so that the image lies in y, i.e., satisfying the defining equations of y. More generally, a map f(x,y) between two varieties is regular at a point x if there is a neighborhood u of x and a neighborhood v of f such that fv and the restricted function f, u, v is regular as a function on some affine charts of u and v. Then f is called regular, if it is regular at all points of x. Note: it is not immediately obvious that the two definitions coincide. If x and y are affine varieties, then a map f(x,y) is regular in the first sense if and only if it is so in the second sense. Also, it is not immediately clear whether a regularity depends on a choice of affine charts. This kind of a consistency issue, however, disappears if one adopts the formal definition. Formally, an algebraic variety is defined to be a particular kind of a locally ringed space. When this definition is used, a morphism of varieties is just a morphism of locally ringed spaces. The composition of regular maps is again regular, thus, algebraic varieties form the category of algebraic varieties where the morphisms are the regular maps. Regular maps between affine varieties correspond contravariantly in 1-to-1 to algebra homomorphisms between the coordinate rings. If f(x,y) is a morphism of affine varieties, then it defines the algebra homomorphism where are the coordinate rings of x and y. It is well defined since is a polynomial in elements if. Conversely, if is an algebra homomorphism, then it induces the morphism given by writing where are the images of s. Note as well as in particular, f is an isomorphism of affine varieties if and only if f' is an isomorphism of the coordinate rings. For example, if x is a closed subvariety of an affine variety y and f is the inclusion, then f' is the restriction of regular functions on y to x. See #examples below for more examples. Regular functions. In the particular case that y equals a1, the regular map f(x,a1) is called a regular function, and are algebraic analogues of smooth functions studied in differential geometry. The ring of regular functions is a fundamental object in affine algebraic geometry. The only regular function on a projective variety is constant. A scalar function f(x,a1) is regular at a point x if, in some open affine neighborhood of x, it is a rational function that is regular at x, i.e., there are regular functions g, h near x such that f equals g, h and h does not vanish at x. Caution: the condition is for some pair, not for all pairs. See #examples. If x is a quasi-projective variety, i.e., an open subvariety of a projective variety, then the function field k is the same as that of the closure of x, and thus a rational function on x is of the form g, h for some homogeneous elements g, h of the same degree in the homogeneous coordinate ring of. Then a rational function f on x is regular at a point x if and only if there are some homogeneous elements g, h of the same degree and such that f equals g, h and h does not vanish at x. This characterization is sometimes taken as the definition of a regular function. Comparison with a morphism of schemes. If X equals spec A and Y equals spec B are affine schemes, then each ring homomorphism phi BA determines a morphism by taking the preimages of prime ideals. All morphisms between affine schemes are of this type, and gluing such morphisms gives a morphism of schemes in general. Now, if X, Y are affine varieties, i.e., A, B are integral domains that are finitely generated algebras over an algebraically closed field K, then, working with only the closed points, the above coincides with the definition given that #definition, i.e., this is immediate. This fact means that the category of affine varieties can be identified with a full subcategory of affine schemes over K. Since morphisms of varieties are obtained by gluing morphisms of affine varieties in the same way morphisms of schemes are obtained by gluing morphisms of affine schemes, it follows that the category of varieties is a full subcategory of schemes over K. For more details, see also http://math.stack-exchange.com/questions/1010388/what-means-this-notion-for-scheme-morphism ? Examples. The regular functions on n are exactly the polynomials in n variables, and the regular functions on Pn are exactly the constants. Let X be the affine curve. Then, is a morphism. It is bijective with the inverse. Since G is also a morphism, F is an isomorphism of varieties. Let X be the affine curve. Then, is a morphism. It corresponds to the ring homomorphism, which is seen to be injective. Continuing the preceding example, let U equals A1, 1. Since U is the complement of the hyperplane T equals 1, U is affine. The restriction is bijective, but the corresponding ring homomorphism is the inclusion, which is not an isomorphism, and so the restriction F, U is not an isomorphism. Let X be the affine curve x2 plus y2 equals 1, and let then F is a rational function on X. It is regular despite the expression, since, as a rational function on X, F can also be written as let X equals A2. Then X is an algebraic variety since it is an open subset of a variety. If F is a regular function on X, then F is regular on and so is in. Similarly, it is in. Thus, we can write where G, H are polynomials in K, X, Y. But this implies G is divisible by Xn, and so F is in fact a polynomial. Hence, the ring of regular functions on X is just K, X, Y. Suppose by identifying the points with the points X on A1 and infinity equals. There is an automorphism sigma of P1 given by sigma equals, in particular, sigma exchanges 0 and infinity. If F is a rational function on P1, then, and F is regular at infinity if and only if F is regular at 0. Taking the function field K of an irreducible algebraic curve V, the functions F in the function field may all be realized as morphisms from V to the projective line over K. The image will either be a single point, or the whole projective line. That is, unless F is actually constant, we have to attribute to F the value infinity at some points of V. For any algebraic varieties X, Y, the projection is a morphism of varieties. If X and Y are affine, then the corresponding ring homomorphism is where properties. Morphism between varieties is continuous with respect to Zariski topologies on the source and the target. The image of a morphism of varieties need not be open nor closed. However, one can still say, if F is a morphism between varieties, then the image of F contains an open dense subset of its closure. Morphism F, X, Y of algebraic varieties is said to be a dominant if it has dense image. For such an F, if V is a non-empty opened affine subset of Y, then there is a non-empty opened affine subset U of X such that Fv and then is injective. Thus, the dominant map F induces an injection on the level of function fields. where the limit runs over all non-empty opened affine subsets of Y. Conversely, every inclusion of fields is induced by a dominant rational map form X to Y. Hence, the above construction determines a contravariant equivalence between the category of algebraic varieties over a field K and dominant rational maps between them and the category of finitely generated field extension of K. If X is a smooth complete curve and if F is a rational map from X to a projective space Pm, then F is a regular map XPM. In particular, when X is a smooth complete curve, any rational function on X may be viewed as a morphism XP1 and conversely, such a morphism is a rational function on X. On a normal variety, a rational function is regular if and only if it has no poles of codimension 1. This is an algebraic analog of Hartog's extension theorem. There is also a relative version of this fact, see Morphism between algebraic varieties. That is, a homeomorphism between the underlying topological spaces need not be an isomorphism. On the other hand, if F is bijective birational and the target space of F is a normal variety, then F is biregular. A regular map between complex algebraic varieties is a holomorphic map. In particular, a regular map into the complex numbers is just a usual holomorphic function. Morphisms to a projective space. Let be a morphism from a projective variety to a projective space. Let X be a point of X. Then some ith homogeneous coordinate of F is non-zero, say, I equals 0 for simplicity. Then, by continuity, there is an open affine neighborhood U of X such that is a morphism, where Y are the homogeneous coordinates. Note the target space is the affine space M through the identification. Thus, by definition, the restriction f, U is given by where G's are regular functions on U. Since X is projective, each G is a fraction of homogeneous elements of the same degree in the homogeneous coordinate ring K, X, of X. We can arrange the fractions so that they all have the same homogeneous denominator, say F0. Then we can write G equals phi F0 for some homogeneous elements phs in K, X. Hence, going back to the homogeneous coordinates, for all X in U and by continuity for all X in X as long as the phs do not vanish at X simultaneously. If they vanish simultaneously at a point X of X, then, by the above procedure, one can pick a different set of phs that do not vanish at X simultaneously. In fact, the above description is valid for any quasi-projective variety X, an open subvariety of a projective variety, the difference being that phs are in the homogeneous coordinate ring of. Note: the above does not say a morphism from a projective variety to a projective space is given by a single set of polynomials. For example, let X be the conic in P2. Then two maps and agree on the open subset of X and so defines a morphism. Fibers of a morphism. The important fact is, Theorem, let f, x, y be a dominating morphism of algebraic varieties, and let R equals dim x, dim y. Then for every irreducible closed subset W of y and every irreducible component Z of dominating W, there exists a non-empty open subset U in Y such that and for every irreducible closed subset W of Y intersecting U and every irreducible component Z of intersecting. Corollary, let f, x, y be a morphism of algebraic varieties. For each x in X, define an irreducible component of containing then E is upper semi-continuous, i.e., for each integer n, the set is closed. In Mumford's Red Book, the theorem is proved by means of Noether's normalization lemma. For an algebraic approach where the generic freeness plays a main role and the notion of universally catenary ring is a key in the proof, see Eisenbud, ch. 14 of commutative algebra with a view toward algebraic geometry. In fact, the proof there shows that if F is flat, then the dimension equality in 2 of the theorem holds in general. Degree of a finite morphism. Let f(x,y) be a finite surjective morphism between algebraic varieties over a field K. Then, by definition, the degree of f is the degree of the finite field extension of the function field K over f asterisk K. By generic freeness, there is some non-empty open subset U in Y such that the restriction of the structure or sheaf Ox to f-1 is free as OI U module. The degree of f is then the rank of this free module. If f is étale and if x, y are complete, then for any coherent sheaf f on Y, writing chi for the Euler characteristic, in general. If f is a finite surjective morphism, if x, y are complete and f a coherent sheaf on Y, then from the Leray spectral sequence, one gets. In particular, if f is a tensor power of a line bundle, then and since the support of has positive codimension if Q is positive, comparing the leading terms, one has. If f is étale and K is algebraically closed, then each geometric fiber f-1 consists exactly of Dage points.